As virtual reality technology expands across domains such as gaming, e-commerce, and networking, the demand for secure, user-friendly, and privacy-conscious authentication is growing. However, achieving secure, efficient, and accurate authentication in VR presents significant challenges. Existing methods are primarily knowledge-based, with one of the most common approaches being pattern-based unlocking, such as that used in MetaQuest 3 or MetaQuest Pro. However, knowledge-based methods are inherently vulnerable to shoulder-surfing attacks, making them less secure in public environments. Behavioral biometric approaches, such as head and eye movements, full body motion, and hand gestures, offer potential solutions but also introduce their own challenges. These methods often suffer from higher error rates and longer authentication times. Recent advancements in two-factor authentication have attempted to improve security and usability by combining behavioral biometrics with knowledge-based methods. However, many existing two-factor authentication methods rely on uncommon interactions, such as eye-blink rhythms, which can be difficult to learn and remember. Others depend on controllers, disrupting immersion and limiting the fluidity of interaction within the virtual environment. To address these challenges, we propose CoordAuth, a hands-free two-factor authentication for VR environments. CoordAuth authenticates users through a two-step process. First, by verifying the 3x3 pattern passwords entered via gaze, and second, by analyzing implicit biometric features extracted from head and eye movements. In the VR settings, users interact with a vertically aligned 3x3 grid, where each point is initially represented by a white sphere that turns red upon selection. A red line collects sequentially selected points, and each point can only be selected once per entry. Our pilot study optimized the grid point size to balance ease of targeting with potential psychological effects of oversized objects in virtual reality. Based on this study and the existing literature, we determined the optimal point size to be 3-degree field of view with a heat-test region of 11-degree field of view. Given that eye and hand movements differ significantly from figure-based input, we conducted a study to examine how grid size impacts user input behaviors and to establish UI design parameters. Using a Western subject design, we tested 4 grid sizes: 40, 60, 80, and 100 degree. We recruited 16 participants and instructed them to input 20 pre-designed patterns across different grid sizes. We measured input time, input error rate, and subjective feedback. The results showed that for input time, 40 and 60 degree outperformed 80 and 100 degree. However, in terms of input error rate, the 40-degree grid size was the most error-prone, likely due to increased selection errors in smaller input grids. For subjective feedback, the 40-degree and 60-degree groups demonstrated comparable physical demand and perceived speed while outperforming the larger grid sizes. With the US settings finalized, we then focused on the behavioral biometric factor. To better utilize head and eye movement characteristics, we segmented the time series data into fixation and saccade segments for classification. Specifically, head movement over time is represented by 6 time series: X, Y, Z, yaw, pitch, and roll. Eye movement is characterized by 3 independent degrees of freedom: yaw, pitch, and roll. as eye position is inherently offset relative to the head. We extracted the following feature sets. Feature 1. Raw features, maximum, minimum, mean, median, and variance for each time series. Feature 2. Deviation features. First derivative with respect to time, followed by the same statistical extraction as in feature 1. Feature 3. Spectrum features. Fourier transform was applied to extract spectral energy, spectral centroid, spectral bandwidth, and peak frequency position. And for authentication, we trained 6 widely used classification models. Random forest support vector machine, k-nearest neighbors, multi-layer perception, extreme gradient boosting, and long short-term memory. We recruited 24 participants, instructed them to input 20 pre-designed patterns, and collected their head and eye movement data. The complexity score of the patterns were evenly distributed. Random forest was selected as the final model due to its strong performance and ability to handle complex features effectively. We then fine-tuned the binary classification threshold to balance the trade-off between the false rejection rate and the false accept rate. Additionally, we implement majority voting to enhance the robustness of the final identity verification. To evaluate feature importance, we conducted an ablation analysis which confirmed that using the full set of extracted features produced the best results for both classifiers. To assess CoordAuth's resilience against shoulder-surfing attacks in real-world scenarios, we recruited 16 participants, forming 8 attacker-defender pairs. Each pair took turns attempting to guess the authentication pattern. Out of the 160 attack attempts, only 16 successfully guessed the pattern, resulting in a 10% success rate. Of these, only 1 attempt successfully bypassed the CoordAuth behavioral biometric authentication factor, leading to an attack success rate of just 0.6%. For usability evaluation, we conducted a 2-factor within-subject study comparing CoordAuth against 3 common authentication techniques, 2 bare-handed interaction and 1 gate-based interaction, which is the ablation condition of CoordAuth. We also examined 3 contextual conditions, standing, sitting, and walking, representing typical VR usage scenarios. We measured registration and authentication time, accuracy, and subjective user ratings. The results show that CoordAuth achieved comparable registration and authentication times to commercial baselines. In terms of false rejection rate, CoordAuth performed comparably to the gate-based interaction method while outperforming both laser-based and touch-based authentication across all contextual conditions. Overall, CoordAuth demonstrates strong security, usability, and immersion, making it a promising authentication method for VR environments. For more details, please refer to our paper. Thank you.